Okay, the YouTube streaming should be live. Let's test it briefly. Kajetan, can you see me and or hear me and see the screen?
Yes,
Yeah?
yes.
Okay, perfect. Then I'll let the attendees in. Hi, everyone. Welcome to the open research session. Hi, glad to see you here via YouTube or in Zoom. Hi, Stefan. Hi, Monica.
Nice to
we
meet
are
you guys.
excited to finally see you again in a TA Academy session. And we really have a great program exploring mechanism design for reputation-based voting systems with great guests. Kajetan, Octopus, and myself will share what we have been working on over the past weeks. And hope you'll enjoy it. We are open for questions and have some links to share as well. Let's take a look at the time. Yeah, I think we can start, and I'll keep an eye on the participants. All right, first of all, a brief introduction. The researchers today are Kajetan, Olas, Octopus, and myself. Maybe Kajetan, please start with some words about what brought you here.
Sure. So it's an honor to be here. My story is that I worked as a tokenomics consultant for more or less a year. During the time, I also took the position as a head of product at HackZ, where I designed all the tokenomics and governance and we could say like the economy of the project, how it should work. And currently, I study quantitative methods at Warsaw School of Economics. I'm both into like business and computer science, so like I'm a hybrid of those two words, I would say. And yeah.
Brilliant. Thanks, Kajetan. Octopus, would you also briefly introduce yourself for those who don't know you yet?
Hello, everyone. I'm Octopus. I am a neurodivergent cypherpunk mathematician, and I do a lot of research and thinking related to sharing and crypto economics, block science, FI Treasury protocol, done economic security research with token dynamics, and most importantly, or most, I guess, enjoyably, was the educational wizard for a while at Token Engineering Academy, and I worked with Angela on this reputation-weighted voting project last summer. So greetings, everyone. Nice to see y'all.
Great to have you here again, Octopus. Yeah, and myself, I'm Angela. I founded TE Academy, built the educational program together with Octopus, and we have been working on how to make the achievements in our systems count, for example, in a voting for the Fellowship Prize voting last summer. And over the past weeks, we have been further exploring the full potential of such dynamic network weight scaling mechanism, as we call it, DNS. And in parallel, I'm also working with the folks at GovAccess team, social choice researchers, and simulation engineers on voting designs, for example, for optimism. All right. Today, our topic is reputation systems, and the core idea of reputation systems is these systems are decentralized. They are established and maintained to have trust and credibility or represent trust and credibility without relying on a central authority in crypto systems. And here we combine data to measure, proofs to verify, and mechanisms to quantify reputation in context-specific applications. And today we'd like to present two contexts and two application cases, HackZ and TE Academy. And we thought it would be a good idea to first give you an overview on purpose, proofs, mechanisms, and examples for these two cases. All right. Kajetan, what's the purpose of HackZ's reputation system? You're muted, I think.
Okay, sorry. Okay, so the main purpose is, I would say, to create a system that can track reputation that is measured on a continuous spectrum, and to try to make it a little bit more objective. Though it's of course not entirely not possible in entirety, but yeah, that's one attempt. So the purpose is to yeah, I would say be able to track reputation measured as, for example, points or rating.
And maybe you can give us a quick introduction of what HackZ is to gain a better
Sure. So HackZ is an AI project that aims to create an AI model that generates mini games, which teach blockchain programming. So specifically writing smart contracts on Aleph Zero or in Rust. And so the way these mini games generated by our AI model are supposed to work is that they are challenges between players. So an AI model generates a game, and then two players at the same time compete who solves it faster, and there is one winner. So that was pretty much the inspiration for. I mean, the rating systems like ELO or Pico2 are pretty natural to implement here, but that sparked the thought that maybe we could also extend it to governance system.
Okay, cool. For comparison, TE Academy's purpose or the reputation system's purpose is that TE Academy is a learning organization. So it's about passing exam, providing lectures as well, creating courses or running peer-to-peer study groups or providing lectures in cohort-based programs. And for all these contributions to the system, we mint NFTs. And the idea for our reputation system is to grant these NFTs voting weight for taking decisions where expertise matters. And since expert and high expertise knowledge in token engineering is scarce, since this discipline is in its early stage, we had to find a good reweighting mechanism. One token, one vote wouldn't work in our case. So it's not only about accumulating as many NFTs as possible, it's also about what these NFTs, what level of knowledge this NFTs represent. All right. When it comes to proofs, how do ecosystem agents prove reputation in HackZ system, Kajetan?
Sure. So we use a combination of tokens and reputation for voting. So tokens are held on wallets. So this is a pretty established standard in terms of security. And with regards to reputation, I think that's the biggest strength of using rating systems like ELO or Pico2 or another system where rating or the reputation is logistically distributed or normally distributed. Is that by design, there cannot be too many people who have high voting power due to having very high rating. Because the way these systems works is that if everybody had high rating, then the average rating would be higher. And we look at the how many standard deviations above the mean is someone's rating. So that's the proof that unless there's some clever, I would say, engineering from the and like exploiting the time discrepancies, then that system is pretty much secure because the rating systems adjust themselves.
Right. In comparison, in TE Academy's case, achievements are proven by ERC 1155 NFTs held in the community members' wallets. And these NFTs are not transferable and are bound to IDs who are unique. and that makes our system highly Sybil resistant, because we only have a certain combination of NFTs and an ID, which is unique in our ecosystem. Okay, mechanism. Can you give us just a brief introduction on the idea how you define reputation and measure reputation in your system, Kajetan?
Sure. So maybe I'll start with how we measure reputation. So the central claim of the system is that the majority of decentralized applications do have activities that they want users to perform that can be represented in terms of like win-lose activities through the rating systems. So, for example, for example, Token Engineering Academy had questions in the well or not, then these questions may also have a rating on their own, and they lose rating or they gain rating, same as players when they play against each other. So, so the way this mechanism works is if it's possible to introduce a PvP rating system, like for example in, I don't know, Counter-Strike or League of Legends, then sure, we can do that, and that works well in terms of measuring rating and reputation. We treat it as the same thing. And when it's not possible, when there's no PvP, then users compete against, we could say, tasks or challenges that also have the rating on their own and balance the system.
Cool. In our case, in TE Academy's case, we had, let's say, a standard rating on the NFTs established by the community. And then we weight according to scarcity, or re-weight according to scarcity in the network. And as a result, the weight of an individual wallet with a certain collection of NFTs held depends on how the overall network grows in terms of achievement and expertise. And I continue with an example. So in TE Academy's case, reputation is gained by passing an exam for an online course, by knowledge sharing, like providing peer-to-peer learning sessions, by creating fundamental knowledge, writing papers, and we define certain levels of expertise or categories in our ecosystem. And once we analyzed the current ecosystem, we understood that only 3% of the NFTs held of the NFTs in existence represent solid, and the reweighting aims to grant equivalent voting weight to the different stakeholder groups we defined, and depending on scarcity of the NFTs that are assigned to these categories, the NFTs gain in weight and are rescaled. How does this work in your case?
Sure. So in the case of HackZ, it's unfortunately untested, so I can't give too much empirical evidence that it works. But the way it's supposed to work is that people play these challenges. They kind of resemble like game of online chess, where just two people compete with each other. Each start with some rating, and at the beginning the rating volatility is high, then it lowers down, and essentially when the players already have established ratings, so it means the volatility is low because we can be statistically sure that that their rating is pretty close to their actual strength, or I would say commitment to being engaged in our community and in our ecosystem. Then we look at how many standard deviations or like rating deviations these players are above the mean of all players. We look at how active they were in the current season, and we basically compute it and multiply it by how many tokens they have. So it's linear with tokens, but not linear with rating.
Right. And I think we should dive into the details of HackZ's mechanism. You prepared some slides to give a more detailed introduction of how this works. Should I skip the slides, or do you want to take over, Peter?
If it's okay, you could.
Okay.
Maybe skip them. Thank you. Okay, so I started with the data from the pretty current research about the centralization of DAOs, and there's a lot of research on why DAOs are centralized and how much they are centralized. But I thought that this one was pretty interesting because it's very much underlined that reputation-based DAOs or voting systems actually are decentralized much more than the token-based systems. The researchers put very high emphasis on it, that they had to kind of use the median instead of mean, because the reputation-based systems like skewed the data. So that's one interesting conclusion, that it's the token-based systems that have the problem. And the other thing that is interesting is that usually it's the big DAOs that are centralized. And it's not that just that they are centralized, but they are extremely centralized, like compared to DAOs with between 100 and 1,000 voters, and like the ones, at the bottom of the table, there's a big difference. And this matters because when there's a lot of voters and there's a lot of activity, I mean, maybe in this case, not activity, but a lot of voters, then we can successfully apply all the rating system stuff and be sure that the math will actually work because the assumptions are satisfied. So yeah, that's the reason to use that we're able to use rating systems in the first place. Okay. All right. So the next idea is that now we showed that we're probably able to use the system because there's a lot of players and the properties or assumptions necessary are satisfied. But now, why would we want to use it? So first of all, when there's a large pool of players, then also the properties like there's a I would say heavy tails are not so heavy, or they're less likely to be many outliers that could potentially corrupt the system. So with large DAOs, using systems based on logistic distribution or normal distributions is a decent idea. And the second thing is that if we make the voting power like multiplication factor rise exponentially along with rating, then we can also be sure that the most engaged users get the most voting power boost, and because it rises exponentially, and also we can be sure that there will be few of such players, because that's how it works if there's a lot of players and the distribution more or less resembles the normal or logistic distribution. Okay, and it's the another reason, but maybe I will elaborate on it a little bit more later, is that it's hard to perform Sibley attack, because if there's a lot of players and we cap, for example, the number of tokens that one can like multiply through reputation at, I don't know, $10,000, then if the capitalization of the project is, let's say, $20 million, because that's pretty normal in crypto currently, then actually the attacker would have to create a lot of fake accounts, would have to spend a lot of time or hire people who would have to smurf them, and even then we could actually just require KIC to to prevent that if we knew that something was happening. All right. Okay, so now we go to the specifics and the math. So to break this down, the VP is the voting power, so like how many votes one can cast, and the if you could click, yeah, TI is the number of tokens held by the user. So if user has twice as many tokens, then they have twice as many voting power. And the rationale for this, why we want to actually include the tokens in the first place, is because well, it's mostly the DAOs with tokens that have the problems, and they won't just like put these tokens out of use, and they need some system that will make it easier for them to decentralize. And second is that actually most projects and most funders want to release their tokens because it's a convenient way to fund their projects. So that's what most people decide on. So in not ideal world, we have to adjust for that and make a system that makes these not ideal projects a little bit better. Okay, so the next factor is the like all the stuff related to reputation and the activity. So first of all, C is just some constant, and I chose this for HackZ to be 1.5 because I ran a bit of experiments, and it just seemed to give a decent values for many different combinations of attempts. But here it will probably require more testing if it were to be implemented in a larger protocol, because yeah, that was just my intuition. And so yeah, that's some constants. The next is basically the math way of writing that's how many standard deviations the user is above the norm. So for example, if you could go to slide number 7, then
this one?
No, the previous.
Okay, sorry.
Okay, here. So here, for example, the curve is marked with 1500, 1850, and so on. And this means that the standard deviation is 350. And so what this z factor essentially tells us, or the z-score, is that if a user has 2020 score, that means he's better than I believe 95% of players. And what this means for us is that is 2 standard deviations above the norm, so the z-score is 2. So it's actually pretty simple idea. Okay, and so yeah, the important idea here is that the z-score is in the exponent of the constant. So basically, if 1 standard deviation is above the norm more, then C rises like it's multiplied by C basically. So if C is 1.5, then your voting power just multiplied by 1.5. Okay.
Next.
Okay, and the part with like what we multiply the Z with is the activity part, how we want to ensure that users actually play in the current season, and we're gonna elaborate on that a little bit more in the next slides. Okay, so first of all, the inactivity damping function, I probably could have named that a little bit, more easy to spell, but yeah. So the way this function works is if you could click 2 times. Okay, so the constant kappa is basically, the higher the constant, the more we tolerate inactivity. So if it's 4, or maybe if it's 1, then players who are required to play 2 times more games that to have the same voting power as if it was 2. So it's basically linear in the way, how much games we require the players to play to not dump their voting power. And so the median of there should be median of recent activity of users within the same rating tier. So basically, this means that, first of all, what does same rating tier means? This means that, for example, if you rated, I don't know, 1800, then we want to look only at players that are rated between 1450 and 2100 and 50, because that's your more or less rating tier. Of course, we could adjust it, like maybe 1.5 standard deviations based on how it works in practice. But the idea is to look at those players, look at how many games they played in the current season, take the median of it. So, for example, these players have had a median number of played games equal to, I don't know, 10. And and we just this function is actually pretty simple. It just takes the set of number of games played by each of those players within your rating tier, and it divides by the median. And yeah, you could click once again. All right, so that's a pretty typical logistic function, and there's more like symbols than numbers, but it's actually also pretty simple because, well, first of all, let's say the median number of played games by users within your rating tier is 10. The constant is 2 because, I don't know, we say so, and we experimentally decide that this is the way to go. And I believe 2 was also somewhere around where I set it, when I experimented. So the inactivity dumping function is equal to 2 divided by 10, so 1/5 or 0.2, and the minus g. So what is this g? The g is number of games that you have played. So if you have played, I don't know, 7 games in this season, then this would be we substitute the for g the 7, for this function we substitute 0.2, and we get some number between 0 and 1. In this case, that would be, well, I'm not sure how much, but I would say that probably like 0.8, like judging from my intuition. And okay, so that's basically, so what is this saying? If you had played more games than 7, for example, I don't know, 20, then this number would be higher than, yeah, I mean, we might want to compute it, but let's say the 0.8. Then this number would be higher than 0.8. And basically, we later use this activity component to multiply it by the z-score. So the higher it is, the better. So the more games you play, the better for you. The more the more voting power you retain, or the less you lose for not playing the current season. But as you play more games in the current season, then it matters less and less. So that's why the logistic function was, I think, a pretty decent choice for this. Because yeah, if you play like, I don't know, 2 games, then it might be 0.4. So like your So your voting power won't be dumped completely, but quite a bit. But on the other hand, if you play a lot of games, like, I don't know, you're addicted to internet and so on, then it will be close to 1, but your voting power won't be boosted by it. It just won't be decreased. So yeah, we can now go to. So here's an example, because if without influence, we can go back to the original equation for the voting power to sum it all up. But here is just example of how we would compute it. So and this is, by the way, generated for ChatGPT, so I hope formatting is okay. So yeah, the tokens somebody has is 100. Let's say I don't know 100 Axie Infinity tokens. Z-score is 1, so the player is pretty decent. He's better than how much? I think 85% of players. But yeah, I think this is the number. And the activity G is he played 25 games. You could imagine, like, I think online chess is pretty good analogy, because, and more specifically, online chess puzzles, where you play against the puzzle, which also has its rating. And imagine you played 25 chess puzzles online. The dumping factor, 0.1. So here we basically skipped the calculation of how exactly it came to be 0.1. But if the k, so the constant, was set to, I don't know, 2, and the median number of games was equal to 20, then like by median number of games by players rated similarly to you, then it would be 0.1, which I think is pretty reasonable. Like 20 games played as median seems like a value that could be true. And the base constant C, so that's the one that's later that's at the bottom of the exponent. So like a C to the power of all this large expression is that part related to reputation. So first of all, the logistic activity term. So we see that this player played 25 games recently, and the median number of games would be 20 if the k was 2. So he played a bit more games than median. He played 25, the median was 20. So his voting power shouldn't be dumped too much. So it's 0.924. Then we compute the exponent. So the z-score, so 1 standard deviation above the norm, times 0.924 is just 0.924, and then we take VP equals 100. That's how much tokens we have, times 1.5, because that was the C constant, and which is equal to 1.5. Just because we said so, we could set to be higher, we could set it to be lower, and basically, if we set it to be higher, like, I don't know, 3, then we increase the voting power of like active users of our application. But this also poses the risk that if we don't test it too much, then I can see scenarios in which it's possible to manipulate the system and like do some revolution. If somebody creates 100 accounts at the same time, pays some people to boost them, and actually, like, let's say each of these accounts gets pretty high rating, 3 standard deviations above the norm, and then you have like voting power, like tokens times 30 basically for each of these accounts. So that's risky. 1.5 is less risky because the potential for abuse is less, and therefore I think it's the less this number is, the less testing it requires. So if somebody wants to test this out prior to testing, or just test this out, see how it works, setting C to be 1.5 is something reasonable. So yeah, in this case, the voting power would be 144, and I think that's how it works.
Cool. Oh wait, we have 2 more slides, I believe.
Oh yeah. So that's just use cases. That's pretty simple. So one is now Axie Infinity. That's like the most obvious case where we have PvP system. The rating system is like already implemented, and you could, like, I guess code it in one evening, and actually test this idea out to see whether it improves the decentralization with the mindset of like rapid iteration and checking what works, what does not. So GameFi is pretty obvious case. And the next one is the example I gave with online chess. So I don't know if any of you plays like on Lichess or Chess.com, but when you have puzzles there where you solve like chess problems, actually each of these problems has the exact same rating as if you were playing against a normal player who had a rating. And if you lose against that problem, I mean you solved it incorrectly, then that problem gains points and you lose points. And the opposite also applies. So I mentioned this because when there's no PvP system or GameFi or anything like that, there's always some tasks or challenges, or like in the case of the TE Academy, like exam, where you can actually assign ratings to problems or questions on exam, and users could also have rating, and it would pretty accurately assess their like skill level, because you have a lot of data. Like if they solve 40 questions, then that's a pretty decent like statistical prop. So yeah, or like airdrop problems where people also farm points and so on. This could also be like implemented in the rating system style. Okay, so this is the last slide. Yeah, the core properties is, for one, we measure the reputation on a continuous spectrum. This can be point system, this could be rating. Resistance to Sybil attacks. So yeah, like I said, if we set the C constant rather on a low level, this can actually encourage people to participate in voting because they feel like they have more say, and it's not like they are completely outnumbered by West. So this should have some positive effect without any downsides. And with high C and a lot of testing, this could actually very much decentralize many projects if we ensure that it is secure and like require KIC, where the algorithms detect that something like SUS is going on. And with regards to foster decentralization while allowing the token to retain its governance utility. So yeah, there are a lot of DAOs where the only function of a token is to serve as the governance unit. So we cannot deprive the token of that function in those cases and replace it entirely. So, or maybe we could, but many people don't want, and it's not for us to judge. So for those use cases, this system is also pretty good because it retains token value, because you still need token to have some say. And so that's all.
Awesome. Thank you, Kajetan, for this presentation. We will make sure to share some more links after the session, and the recording is also available. We got some questions about that, so that you can go back to the exact formulas and maybe run some experiments yourselves, everyone, to explore the properties of the system. But for now, let's move on with the second use, or the second case for reputation-based voting, looking at the time. Let's compare this with TE Academy's case. So we try to nail the goal of this reputation system in one sentence. We have the early stage of our network, token engineering, and experts are scarce. for a voting where expertise is necessary to take good decisions, well, we want to make sure that achievements are weighted so that scarce experts have a fair say in voting. This was the original idea. And if you look at these NFTs, these are the badges you can earn. Then, for example, we have 4 NFTs minted to course authors. And if we look at module 1 graduates, we have 243. So that's the relation between those who have been grading the course material versus those who are consuming and learning based on this material. And yeah, again, the reweighting goal is to give proportional and appropriate voting power to these scarce, expert, high-level knowledge in the token engineering sector. All right. Our NFTs, again, are on-chain NFTs ERC 1155. Here's the full collection of NFTs. They are minted for different achievements. And in a nutshell, they are non-fungible, non-transferable. The wallets are tied to a certain ID in our ecosystem. And this unique fingerprint, this unique collection of NFT makes them highly Sybil resistant. Nevertheless, users are in full control, so there is no black box, let's say, complicated computation of weights. It depends on the type of NFTs and how scarce these NFTs are. And by controlling the NFTs, meaning minting and burning, you control your own weight and voting power. Okay, the distribution, if these are numbers, I think from June 2024. And when we analyzed the NFTs minted in our ecosystem, we found that there are 871 that are on a student level, 550 on a graduate level, and only 45 on an expert level. Okay, and again, if you would now establish a voting where you have 1 token, 1 weight, experts would have the least voting power. And the solution or the goal is that we give all 3 categories or stakeholder groups equal voting power and scale up the weights accordingly. And the process of this, how we scaled it, is here. And I hand over to Octopus to give you a brief overview on the steps involved.
Thank you, Angela. So, as was mentioned just now, we have these credentials, and one interesting thing is you may choose to design new credentials based on prior ones. For instance, when we were looking at voting last summer, the group of graduates were a special group who had achieved successful completion of all 5 TE fundamentals courses. And then after the credentials have been created, they're placed into different groups. Last summer, the groups were student, graduate, and expert. And then we rely on human expert designer to give the credentials some kind of initial weights. So Angela took this role as someone who was most suited to have expertise about which different types of NFTs should be considered most powerful. But then once we have this initial weight that's based on subjective expertise, then we choose a weighting mechanism for how those weights according to different groups will be compared. And the algorithm runs and reweights the credentials so that whatever the weighting constraints are met. This usually involves reweighting the credentials relative to each other, both between the groups primarily. And then we kind of do a check of whether this is a reasonable distribution that we now have. We've rerun the initial distribution and reweighted it according to some intended outcome, like the groups should be equal. And then we look and see, well, what outcomes could happen if we actually use this weight distribution? If those simulation scenarios and KPIs look good, you can use that weight distribution. And if not, you just try a new one. And the goal here is to have something where, as you try new ideas, it's easy to try a new idea, see quickly whether or not you think it's workable, and then try a different one. So it's more on the simulation and less on the math for this particular approach. Would you go to the next slide, please? The key idea here is the C weight, which is the total collective weight of a voter group, which is the weight of all credentials or NFTs of all members in the group. You can use different types of constraints. For instance, you could use ranking, which is what was used last summer, and expert C weight must be at least as much as graduate C weight, and graduate C weight must exceed student C weight. Or you could do a different proportional weighting. You could say something like the experts should have 50%, graduates should have 30%, and the students should have 20%. Next slide, please.
My clicker, give me a second.
And after another aspect of this is after we have done the recalculation of the weight, the reweighting is just math, but we want to be sure that we're not leading ourselves into unacceptable scenarios. So there are some checks you can do on the reweighting. You can look for concentration of power. Like, is there a single account that could completely determine the outcome? How much is power concentrated via what percentage control? 50%, which was also alluded to earlier. That's the Nakamoto coefficient. But we were also looking at the other side, which is too much power dispersed. And so we created this metric called the Swifty number in honor of Taylor Swift, imagining the scenario where Taylor Swift might decide that she has a preferred candidate and sends her army of Swifty fans to vote, and they're just obtaining the easiest to obtain NFT. So this is a metric that calculates potential for abuse or gamification via Sybils or via uninvested community members only joining to manipulate this one outcome. Next slide. We have a code base that goes into where you can see all of the logic as well as some of the demonstrations and simulations and visualizations that were used in making and validating the decision. So I encourage you to check that out. We've discussed that more in a previous session, so we're not going to go into the details at this moment. And then finally, for actually recalculating in the mechanism that was used last year in the summer, it was the maximum of the initial collective weights of the 3 different groups was set as a target. And then each group was rescaled so that it would achieve the desired outcome weight, which made all groups equal. And that calculation, which Angela deserves credit for, was a crucial idea that made the entire mechanism work.
Should I continue?
Yes, it is back to you now.
Okay, thanks so much. Yeah, and here's an example of in the real state of the ecosystem dating from June 2024, how the reweighting then actually looks like. So we have the dark blue. These are the initial weights assigned by the community in a sense. So how to differentiate between different types of NFTs and achievements. And the bright blue is the reweighting result. And as you can see, the first, the NFTs on the top gained a lot of additional voting weight due to the mechanism. And again, this is due to their relative scarcity. And at the lower end of the scale, on the left of the diagram, you see student NFTs who are in high supply with no additional weight gain due to the reweighting mechanism. And similarly, on the right, this chart on the right again shows different NFTs. And the dark line, the NFT supply, and the bright bars, the resulting voting weight. And again, we see NFTs in very high supply on the right have received then, as a result of the reweighting, very low voting power. Okay, and now how, since we applied this mechanism for a real case, the fellowship voting, we analyzed how the voting outcome and the votes of the different NFTs then added to the overall result. And if we look at this diagram here, in dark blue, we have NFTs assigned to the expert level, in green, NFTs assigned to the graduate level, and in yellow, student level. And we see that NFTs assigned to students and graduate actually voted very similar. So we have 4 candidates, and the percentage how much NFTs voted for these candidates. And again, students and graduates voted very similar, while expert had a quite a different opinion on the winning candidate. And due to the reweighting, the candidate 4 actually won in the fellowship voting. So again, make expertise count in a voting. We reweighted, and this had an actual impact on the result. Now we have some minutes left, and I'd like to share some additional steps we are taking at the moment. Over the past weeks, we've been working on an updated version of the scaling algorithm in a team. Tom, who's also here in the call, he's a graduate at TE Academy. Octopus and myself have been exploring the emerging properties of this DNS mechanism with some quite interesting properties to meet the design goals. And for this exploration, we even got rid of setting initial weights. This means K equals 1. So all NFT types are worth the same initial weight. And from there, we scale according to scarcity, so that in a meritocratic system, unique and unprecedented achievements should have highest weight. And an introduction to this idea, and also how we built the whole NFT system at TE Academy, is available on Mirror already. And the next article about the exact mechanism design and the properties we can expect will be published in March. And just some pointers. If we look at this graph, this is showing the NFT supply of only 2 categories in a made-up system. The solid blue and red lines show the supply. So how many NFTs are available in the system, and we iterate and grow the supply as we expected in a regular system. More achievements accumulate in the system. We gain more the total NFT, and also within the categories grow. And then we compare or we calculate the multipliers, meaning the scaled NFT weights of these NFTs. And you can see them in dotted lines. Now, let's review a case where the blue supply is significantly lower than the red supply. So we start with step 1, time step 1, low blue supply and much higher red supply. And when we then only grow, so the red supply remains unchanged and the blue supply is growing step by step by step. And if we look at the multipliers in the dotted lines, we see that the actual NFT weight after scaling of the blue NFTs is decreasing. and until the point where the blue supply is actually higher than the red supply. And then things change significantly. On the blue side, let's look at the blue dotted line. The NFT weights decline hyperbolically. And once the maximum supply of the blue NFTs matches the red NFTs, then the situation changes and the multiplier, the NFT weight after scaling of the blue NFTs doesn't change anymore. It remains the exact same. And if we look at the red dotted line, if the supply of the blue NFTs grows, the red NFTs benefit as soon as the red NFT supply is smaller than the blue NFT supply. So then they start growing in NFT weight. Now let's put this, let's look at this from the perspective of incentive design. So what does this mean for the holders of the NFTs? Minters of the blue NFTs benefit, they have a higher NFT weight only as long as this NFT is in lowest supply. This is perfectly in line with what we intend. Later, no matter how many NFTs are minted, it does not matter anymore. And the NFT holders don't grow their weight anymore. And this is not ideal. It would be better if there would be some peer group pressure. So the more NFTs are minted, the NFT weight declines. That's perfect. But if this decline should continue, the more NFTs are minted. And if we look at the red NFT holders, they benefit as soon as their NFT is in lowest supply, even if NFTs are minted in other categories. And that's interesting because it's an aspect that we actually find really relevant in meritocracies and decentralized systems. Give everyone a share in the growth of value in the system so that they support each other. And particularly in education, it's not a zero-sum game. So it's really relevant that you share your knowledge, that you create activities to also disseminate knowledge. So it should not be competing for knowledge. In fact, everybody should participate and benefit from the growing overall knowledge in the ecosystem. So in fact, benefiting from other categories minting NFTs is good. Now, if we look at the current version, this maximum version and this diagram, we find some things that are great and others that are not so great. And we started, again, nailing 4 key design goals for meritocratic system. Number 1, an incentive for the individuals to learn and make progress. Second design goal, an incentive to support others in making progress. Third, an incentive to maintain high quality standards. And this is actually balancing number 2. So if we make it super easy to mint additional NFTs, the relevance and reputation declines of the knowledge in the system and the proofs. And number 4, design goal 4, incentive to take on hard challenges. So even though you benefit, an individual benefits from proving new achievements, it should be an additional incentive to take on hard challenges or to aim for NFTs that are actually that only a few have managed to receive. All right. And we found some variants of the algorithm that actually reflect much better what we are intending here with the 4 design goals. For example, a version where the target weight of the C weights of all NFTs is the product of C weights. The good thing about this is that if we look at the red dotted line, red NFTs always benefit. So their supply remains the same, but they benefit from other categories gaining and accumulating new achievements, plus, what's bad, the downside of this version is blue NFTs never benefit. So their NFT weight remains the same no matter if we have a very low or a very high supply. And that here we are missing the incentive of if the supply is scarce, people should have a higher NFT weight. So this is the incentive to take on hard challenges. All right. We decided to use the sum variant, which meets all 4 design goals. And just, for example, design goal number 1, look at the blue dotted line. It's always above 0, so it always has a positive effect on your voting weight if you mint new NFTs, if you gain new achievement proofs. Second, support others. If the blue solid line grows, if the NFT supply grows, the red dotted line grows as well, so other categories benefit too. The third design goal, maintain high quality standards. Yes, if the blue NFT supply grows, the NFT weight declines. This creates a peer group pressure to make it not too easy to receive NFTs in the same category. And last but not least, the scarcer the NFT type is in the ecosystem, the highest, if you look at the blue dotted line, with at the very left end, the higher is the NFT weight you can gain. And this is an incentive to take on hard challenges. All right, so this was just a quick primer on the design goals for a super simple algorithm and how this results in certain incentives and align the incentives between individuals and the total ecosystem. And again, take a look at Miro. You can find it at Token Engineering Academy Miro if you Google it. And we also share some links in the notes of the session where we published the first article about the NFT system and the second one about the algorithm. And finally, meet us at EthCC in June to July. The next EthCC is going to take place in Cannes. I hope to see you there. And we'll have great talks about mechanisms like that and design incentives using tokens. And I hope we'll see you there again. For now, first of all, thanks for joining. And if you have any question, shoot it away. I think we have some minutes left for any questions. Okay, this was a lot of content, but we are here. You can reach out to us on Twitter, Talk Engineering, and find also Kajetan and Octopus handle. And feel free to reach out. Always happy to discuss reputation systems. Thanks so much for the session today. Thanks, Kajetan. Thanks, Octopus, and thanks everyone.
Thank you. See you later.
Thank you very much. It
Bye.
was an honor to be here.
The recording has stopped.